the speed at which our universe is expanding. Both use cutting-edge instruments. Both employ rigorous methods. Both are confident in their results. And both cannot be right. One says the universe expands at 67 kilometers per second per megaparsec. The other says 73. That might sound like a small difference, but in cosmology, it's a chasm. Because if both measurements are correct, then something fundamental about our understanding of reality is broken. Let's start with what we know for certain. In 1929, Edward Hubble made one of the most important discoveries in human history. He observed that light from distant galaxies was stretched towards the red end of the spectrum. Not just a few galaxies, all of them. And the pattern was unmistakable. The more distant a galaxy, the more its light was redshifted, and the pattern was unmistakable. The only explanation that fit the data was that these galaxies were moving away from us, not because they were traveling through space, but because space itself was expanding, carrying them along with it. This wasn't philosophy or speculation. It was measurement. It was real. Since then, every observation, every telescope, every advance in astronomical technology has confirmed this expansion. We can measure it with extraordinary precision. Multiple independent methods all converge on similar values. The expansion of the universe is as well established as any fact in science. Yet explaining how it works, what drives it, and why it behaves the way it does remains profoundly puzzling. Here's where most people's mental model starts to break down. When you hear the universe is expanding, you probably think of galaxies flying outward through space like debris from an explosion. That seems logical. It's also completely wrong. The galaxies aren't moving. Space itself is expanding between them. This isn't just semantics. It fundamentally changes what expansion means. There's no center from which everything is flying away. There's no edge you could travel to. Every observer in every galaxy sees the same thing, all other galaxies receding in all directions. If you were in a galaxy 10 billion light years away, you'd see the same pattern. Everything would appear to be moving away from you, just as everything appears to be moving away from us. This is profoundly counterintuitive because it violates our basic sense of how motion works. In our everyday experience, things move through space to new locations. But expansion isn't motion through space, it's the growth of space itself. And it gets even stranger from here. According to Einstein's special relativity, nothing can move faster than light. This is one of the foundational principles of modern physics. It's been tested countless times and has never failed. Yet there are galaxies so distant that they're receding from us faster than the speed of light. How is this possible without breaking relativity? Because those galaxies aren't actually moving through space faster than light. They're essentially stationary in their local reference frame. It's the space between them that's expanding so rapidly that the overall recession speed exceeds light speed. Relativity forbids objects from moving faster than light through space-time, but it places no limit on how fast space-time itself can expand. This creates a haunting reality. There are entire regions of the universe we will never be able to see. Not because they're too far away for their light to have reached us, but because the space between us is stretching faster than light can cross it. These galaxies exist beyond the cosmic horizon, permanently beyond our reach. But the mystery that's currently fracturing cosmology runs even deeper. For most of the 20th century, cosmologists assumed the universe's expansion would gradually slow down. This seemed obvious. Gravity pulls things together, so an expanding universe filled with matter should experience a gentle braking effect. The expansion might continue forever, but it should be decelerating, getting slower and slower over time. In 1998, two independent teams of astronomers studying distant supernova discovered something that shocked the scientific community. The expansion wasn't slowing down. It was speeding up. The universe's expansion was accelerating, and had been for roughly 5 billion years. This discovery was so unexpected, so contrary to theoretical predictions, that it won the 2011 Nobel Prize in Physics for team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees. But winning a Nobel Prize didn't answer the fundamental question: what's causing this acceleration? To account for their observations, cosmologists invoked something called dark energy. But here's what you need to understand. Dark energy isn't an explanation. It's a label for an effect we observe but cannot explain. We can describe what it does mathematically. It accounts for roughly 68% of the universe's total energy content, and it exerts a kind of repulsive pressure that drives space apart. What we cannot describe is what it actually is, where it comes from, why it has the value it does, or how it works. Dark energy is fundamentally a placeholder, a way of quantifying our ignorance while we search for a deeper understanding. And recently that search hit a wall. When scientists measure the universe's expansion rate using the cosmic microwave background, the ancient light left over from the Big Bang, and apply our best cosmological models, they calculate a value of about 67 kilometers per second per megaparsec. That means that for every 3.26 million light-years of distance, space expands by 67 kilometers per second. But when other scientists measure the expansion using observations of relatively nearby stars and galaxies, constructing what's called a cosmic distance ladder, they consistently get a different answer, about 73 kilometers per second per megaparsec. Both groups are using precise, well-tested methods. Both have checked and rechecked their work. Both have ruled out obvious sources of error. And as measurements have gotten more accurate over the past decade, the gap between these values hasn't closed. It's widened. The discrepancy now stands at more than 5 sigma, a statistical significance that, in normal circumstances, would indicate we've discovered something genuinely new. This is what scientists call the Hubble tension, and it's tearing cosmology apart. Because either one of these measurement methods contains a systematic error we haven't identified, or our models of how the universe works are incomplete. There's one more oddity that makes expansion even harder to grasp. If space itself is expanding, why aren't we expanding? Why don't atoms, planets, solar systems, and galaxies grow larger as space stretches? The answer has to do with binding force. Expansion only dominates at the very largest scales, the vast distances between galaxy clusters. Within galaxies, gravity is strong enough to hold stars together. Within solar systems, planets remain in stable orbits. Within atoms, electromagnetic forces bind electrons to nuclei. These local forces easily overcome the expansion. But between galaxy clusters separated by hundreds of millions of light-years, there's not enough gravitational attraction to resist. Space stretches, and the clusters drift apart. This selective behavior is unsettling. Why should a property of space itself, something that's supposedly uniform and universal, turn on and off depending on what's in it? The answer involves complex interactions between gravity, space-time geometry, and energy density, but the underlying strangeness remains. When we say the universe's expansion doesn't make sense, we're not claiming the observations are wrong. The expansion is real, it's measured, it's verified by multiple independent methods. What we're saying is that our explanations remain incomplete. We can measure expansion with remarkable precision. We can track it across billions of years of cosmic history. We can see its effects in every direction we look. But we cannot yet explain why it happens the way it does, why it accelerated when it did, or what dark energy actually is. We have mathematical descriptions that fit the data, but mathematics doesn't provide understanding. This isn't a failure of science. It's science functioning exactly as it should. Confusion marks the frontier of knowledge. Every major revolution in physics began with an observation that didn't fit existing theories. Quantum mechanics emerged from puzzles about how atoms emit light. General relativity arose from contradictions in how gravity and electromagnetism behaved. The standard model of particle physics took shape as physicists tried to explain patterns in particle collisions that shouldn't have been there. The expansion of the universe, particularly its acceleration and the Hubble tension, may be signaling the next revolution. These aren't signs that cosmology is broken. There are signs that something profound is waiting to be discovered. The universe stretches without a center. Distant galaxies recede faster than light. An invisible energy pushes everything apart, and we have no idea why. Two different ways of measuring the same expansion give different answers, and we don't know which one, if either, is telling us the complete truth. These aren't flaws in our observations. They're features of reality that challenge our understanding. The universe doesn't expand the way common sense suggests it should. It doesn't slow down the way gravity says it must. And it doesn't measure the way our models predict it will. But that's precisely what makes this one of the most compelling frontiers in science. The expansion of the universe doesn't make sense yet, but in that yet lies an entire world of discovery waiting to be revealed. The answers are out there, written in the light of distant galaxies and the structure of space itself. We just have to figure out how to read them.